Hello, today we're going to discuss the practice test. I put the key out there already for those of you who asked for it, but I also kind of wanted to go over it too. So here we have problem number one, which is a titration at different stages. And so you are taking benzoic acid and reacting it with a strong base, sodium hydroxide. Now, the very first one, you haven't added any sodium hydroxide, so the only thing you have is the acid dissociating. And the Ka of the acid is given to you as 6 times 10 to the minus fifth. So I have written the equation here, and if we start with 0.100 here, and then we have 0 and 0 of the products, we're going to add x and x and subtract x from the 1-to-1-to-1 ratio we have. We can see that 6 times 10 to the minus fifth and 0.1, 10 to the minus 1, certainly we can estimate. So I did away with all of the minuses. So we get x squared over 0.100 is equal to the Ka. So take 6 times 10 to the minus fifth times 0.1, square root it, and that's going to give you the hydrogen ion concentration of 2.5 times 10 to the minus 3, and then log that and change the sign, and you get a pH of 2.6. I really should have another sig on that. Sorry about that. Now we're starting the titration. We're going to add 10 milliliters of the 1/10 molar hydroxide. So I take 10 times 1/10, and that's what gives me the 0.1 millimoles. And then I still have my 30 milliliters of 0.1 molar. So that gives me 3 millimoles. So I'm going to consume all of the limiting reactant, which is the base at this time. And so I'll have 0 hydroxide. I will have 2 millimoles of acid and 1 millimole of the conjugate ion. And so this means that I really should be looking at the Henderson-Hasselbalch reaction here because I have leftover acid and conjugate. That means I'm going to use Henderson-Hasselbalch, and so that's what I have set up over here. And you end up with this concentration for X, and so that gives you a pH of 3.9. So the pH is going up, as it should if you're adding hydroxide. And then we're going to go up to 30 moles. So we've added 30 moles of each ingredient. So we're both at 3 millimoles, since they're both 1/10 molar concentration originally. So they both get consumed, and the only thing I have left is the conjugate. That means I'm going to have to take the conjugate and see how it hydrolyzes with water, and I'm going to make it, it is going to be a strong conjugate base, so I'm going to make hydroxide. And so I'm going to get, I have to calculate the Kb of this reaction, so I'm using Kw divided by Ka here. And that gives me this value. And then my equation will be, these are x squared all over 0.05. And so I'm going to take my Kb times 0.05, square root it, and that will give me the hydroxide concentration. So I get the POH and then the pH. And you can see I didn't subtract right the first time. I'm terrible about that. Sorry. Notice how close it is to being neutral. And it is, if you take a look at this concentration of hydroxide, it's very near what it would be in water, which is 1 times 10 to the minus 7th. And so that's why you just have a pH just slightly over that of water. And then our last one, we're actually adding too much hydroxide. And so I have a millimole of hydroxide left. That's going to drive the pH here. And so I calculate my hydroxide ion concentration. It's 1 millimole, and I've added a total of 70 milliliters, 30 of acid, 40 of base. And so I get 0.014. And so I take the POH of that and get 1.8, which gives me a pH of 12.2. The next problem, I am given a silver chromate and silver chromate decomposes to 2 silver ions and 1 chromate ion. I'm given the KSP value. So since this is 2x and this is x, I'm actually going to end up with 4x cubed here. And so to get the final answer, I'm going to take my KSP divided by 4 and then cube root it to get this concentration as the molar solubility of the ions. Number 5, I am looking at a ratio. So I'm using Henderson-Hasselbalch. So I want a pH of 3.5. I look up my Ka of hydrofluoric acid, and that gives me this when I look it up. So that gives me this pKa. So I take 3.5 minus 3.1 and get 0.4 is equal to log x. So 10 to the 0.4 is equal to x, so x is 2.5. So this means I have a 2.5 salt ratio to acid for every 1 acid. So that means that could be 2.5 molar to 1 molar. It could be 0.25 molar to 0.1 molar. Again, it just depends on how bad you want it to have a good buffer against it. So the stronger the concentration in that ratio, the more it'll take to swamp the buffer. You won't be able to overcome the buffer. And so I hope this gets you ready for the test. You can see the test is going to be worth point-wise 35 points, but you will, as always, get your percentage score.